Welcome to the Forces Part 3 tutorial. Before we do anything else, let's see what you remember from 1 and 2. Take a second, pause the tutorial, and see if you could name each of the forces that are drawn on this diagram. F1, F2, F3, F4. Okay, hopefully you've done that. And I hope that you were able to identify all four forces. The first force, F1, is an applied force being put on this block, and it's labeled M, probably for mass, because we call an object in physics that we're trying to move a mass. So the guys are pulling on it, and that's an applied force, right? Then from the bottom, F2, the table pushing up against this mass, is the normal force. F3 is the force of gravity pulling the block down, and F4 would be the force of friction resisting the applied force. So you can see that the gentlemen are pulling to the right, friction is resisting that pull to the left, gravity's pulling down, and the normal force is pushing up. Now what we want to consider is what's going to happen if that applied force is greater than the force of friction, or if the force of gravity is greater than the normal force. What will happen is that the object, the mass, will accelerate. And by that we mean its speed or direction is going to change. And if the guys are pulling hard enough, they'll be able to make that block start to move to the right. If the table isn't strong enough, gravity will be able to pull it down through the table and smash it to the ground. We haven't really talked about the word acceleration a lot yet, and it's time now for you to start thinking about what this word means and compare it to the words speed and velocity. Most of you seem to get the idea that speed and velocity are basically the same thing, except that velocity includes what direction you're moving in. Acceleration is different. Acceleration refers to changes in your velocity. So you're accelerating if you're speeding up, slowing down, or changing the direction you're moving in. And it's important that you recognize that as being different than just speed or velocity. Forces cause accelerations, and we can actually measure how much force is put into an acceleration. And we can do that, one of the ways we can do it is by using this device over here on the left called a spring balance, sometimes also referred to as a spring scale. Technically, balances and scales measure different things, but it doesn't matter for right now. So your spring balance works like this. You can kind of see in this picture over here that you can dangle a weight from that little hook, and you can see how much the spring, you can see the little spring here, how much that spring is pulled down by the force of gravity. And it's measuring that pull in units called newtons, named after Sir Isaac Newton. And these units, these Newton units, are what we call SI units. SI stands for System International, which is the French way of saying international system. There is a scientific set of units that most scientists, if not all, agree to use all the time, and it's called the SI system, or Système International, so that no matter where you go in the world, if you're working scientifically, you're all using the same units, and that makes life a lot easier if you do that. So the scientific SI unit for force is the Newton. So unfortunately for you guys, you probably never measured anything in newtons before. You probably have never measured a force before in your life. You just sort of talk about forces in terms of harder or softer, right? I hit that baseball really hard, or I hit it really lightly, or I pushed the box as hard as I could, or I really put my weight into it. So you've never actually measured a force. So this is going to be a new thing for us. When we measure in newtons, I want you to have a sense of what a newton is equivalent to. So the best way I can do that is to kind of compare newtons to pounds, which you are familiar with. So weight is measured on Earth in pounds, at least here in America. Other places we use other units like kilograms. So if you think of it this way, imagine you're holding a 1 pound object in your hand, and you can feel the force of gravity pulling it down. Well, how many newtons is that? Well, 1 pound of force is roughly approximately equal to 4.5 newtons of force. That's just to give you a rough idea. And we abbreviate newtons with a capital N. And this squiggly looking equal sign means approximately equal to, not exactly equal to, because I rounded to 4.5. It's like 4.4445 or something like that. In these pictures, you can see that you don't have to use a spring scale or a spring balance to measure just weight. You don't have to use it just for the force of gravity. You could also use it to measure an applied force. Or I like this particular picture here, which shows that you can measure something called the buoyant force. You've probably heard of buoyancy, right? When things float, we say that they're buoyant. You may even have heard of the word buoy, which comes from the same root, which is an object that's floating in the water to mark the way. The buoyant force is that force you feel when you're in water. As you get into the water, you can sense that you seem to be almost like losing weight. If your friend wanted to pick you up, it would be easier for your friend to do that in water than it would be on land. And that's because the particles in the water are actually moving, and they will collide with the body and push the body up, and that's called the buoyant force. You can measure the buoyant force with a spring scale by lowering it into the water. You can lower your weight into the water. And it may not float, but it'll still experience a push upward from the water that'll show up on your spring scale. So you'll be able to compare what the weight pulls down in weight and how it pulls down in water. And the difference between the two would be this thing called the buoyant force. So we can measure forces with spring scales. You can also hook up a lab quest to something called a force plate, or I also have some other types of things you can hook into a lab quest that'll measure force. But the spring scale is kind of the old trusty way of doing this. I want to talk for a second about a misconception that a lot of people have about forces, and it comes from this word G-force. A G-force is badly named. G-forces are not actually technically forces, they are accelerations. When you are accelerating, for example, on something like a roller coaster, I'm not really sure what this guy is in, maybe he's in an airplane, but wherever he is, he's experiencing G-forces, and what they are those pushes and pulls that you seem to feel when you're moving really, really fast in a particular direction or changing direction really quickly. And G-forces are actually called G because of gravity. G stands for gravity. And a G-force is a measurement of the acceleration that you normally feel when you're in a gravitational field. Here on Earth, when you're sitting in a chair or standing up or whatever you're doing, gravity is trying to pull you down to the center of the Earth. So the normal force of whatever you're standing on or sitting on is pushing back up against you. So gravity's doing this, and something is pushing you back up, and you're pretty much standing or sitting still. So you're experiencing what's called 1g of force from gravity right now. It's not actually a force, it's an acceleration. It's how quickly that gravitational field is trying to make you speed up. If you were in a roller coaster and you were coming down a big hill like this, and let's say you were going faster than gravity would just pull you, well, then you would begin to feel extra acceleration on your body. And that extra acceleration would mean that you're moving faster than the rate that you normally move under the influence of gravity. And you might call that a 2g acceleration, which would just mean that you're moving at you're accelerating at twice the rate that gravity would accelerate you. And you would need an engine or a push or something to make the cart do that would have to be not just under the influence of gravity. So this guy's face is making all kinds of weird contortions because he's under the influence of acceleration, not forces.